Okay, so recently I stumbled upon this very beautiful Fibonacci sum. So it looks like this. So it's the sum from n equals 0 to infinity of 1 over 1 plus the odd Fibonacci numbers. So I had never seen this sum before, and notice I haven't told you what the sum is yet, so we're going to get to that. So I thought I'd make a video about it. So I've cooked up one solution that uses the closed form of the Fibonacci numbers, but I thought that that was like not maybe as beautiful as I wanted it to be because it uses all of these square roots of 5 and all this kind of stuff throughout the calculation. And if that exists, it'd be nice to just see it at the very end of the calculation. So I came up with another solution, and it uses the following lemmas. So this first lemma, so that says the nth Fibonacci number times the n plus first minus the m plus first times the nth. So that's equal to minus 1 to the n and then f sub m minus n. And then next we have lemma 2, which is well known. Usually it's written in the other way as a reciprocal, but it says that the limit as n goes to infinity of the nth Fibonacci number over the n plus first is equal to minus 1 plus root 5 over 2. So I'm going to go ahead and prove these lemmas first before we dive into what this sum is. So let's look at the proof of lemma 1 first. Okay, so we're going to prove this by induction. So what we want to do is fix an m and then use induction on n. And so our base case will be the case when n equals 0. And this case is like very, very obvious. So here we get fm f1 minus fm plus 1 f0 equals minus 1 to the 0 f of m minus 0. But notice f of 0 is 0, so this term turns into 0. And then f of 1 is 1, so we can replace that with 1, and notice the left-hand side and the right-hand side of the equation are the same, so we're okay. Okay, so now let's make an induction hypothesis, and this is actually a strong induction hypothesis, so we'll write it as follows. So let's suppose for all r less than or equal to k, we have this statement is true where n is replaced with r. So we have fm fr plus 1 minus fm plus 1 fr equals minus 1 to the r fm minus n. So what I mean here is that for all values that we plug in less than or equal to k, this statement is true. So it's true if we plug in k, it's true if we plug in k minus 1, and so on and so forth. So like I said before, this is sometimes called strong induction, but regular induction and strong induction are equivalent. So it's really no big deal one way or the other. And now what we're going to do is look at the k plus first version of this left-hand side. So let's see what we get if we plug in k plus 1 for r into the left-hand side. So we'll get fm fk plus 2 minus fm plus 1 fk plus 1. And now notice that is not covered by the induction hypothesis, so we need to work with it a little bit. So that's going to be fm, and now let's use the Fibonacci recursion on this guy right here. So that's going to be fk plus 1 plus fk. Okay, good. And then now notice we're going to have minus fm plus 1, and then again we'll use the Fibonacci recursion on this as well. So we get fk plus fk minus 1. Okay, fantastic. So now what we'll do is we'll rewrite those things, so reorder them a little bit, and we're going to do that as follows. So let's write this as fm k plus 1, so that would be that term and that term, and then minus fm plus 1 fk, so that would be that term and that term. Okay, good. And then we'll have plus fm fk, so that's that term times that term, and then minus Fm plus 1, Fk minus 1. Okay, good. And then that's obviously this term times that term. Okay, and now what we have is both of these things in parentheses are covered by our strong induction hypothesis. Notice this first one is our strong induction hypothesis with R equals K, and the second one is our strong induction hypothesis with R equals K minus 1. So that means we can apply our strong induction hypothesis to write this as follows. So this is minus 1 to the K power of Fm minus K. So that's the first one. And then plus minus 1 to the K minus 1 power of M minus K plus 1. And so why is it minus K plus 1? Well, that's because it's M minus the quantity K minus 1, because this is this statement with R equals K minus 1. So the next thing I can do is factor out a minus 1 to the K plus 1. And now notice that minus 1 to the K plus 1 and minus 1 to the K minus 1 are the same. And so what that is going to leave me with is negative Fm minus K plus Fm minus K plus 1. Okay, so that's going to give us that. But now notice by our defining relation on the Fibonacci recursion, just this thing rewritten a little bit, that's going to be exactly minus 1 to the K plus 1 times Fm minus K minus 1. Which is exactly what we want it to be, because that looks like what we should have for the K plus 1 version of this equation, which finishes the proof. Okay, so that means we are done with the proof of lemma 1. So I'll clean up the board and then we'll move on to the proof of lemma 2. Okay, so now we're ready to do this proof of lemma 2. So we're going to do this using the monotone sequence theorem. Okay, and that says that if we have an increasing sequence or a decreasing sequence, so a monotone sequence that is bounded, then it must converge. So the first thing we need to show is that this thing is bounded. So let's see how to do that. So notice that all of these terms are positive, Fn over Fn plus 1, and that's because all the Fibonacci numbers are positive. But now what we can do is rewrite the numerator as follows. So this is Fn plus 1 minus Fn minus 1 over Fn plus 1. So that's just rewriting the normal Fibonacci recursion kind of in an obvious way. But now notice that's going to give us 1 minus Fn minus 1 over Fn plus 1. Good. But now notice this term is bigger than 0, so we're taking something that's bigger than 0 away from 1, so that means that this is less than 1. So that means our sequence is bounded between 0 and 1. And so the next thing that we'll do is show that this is monotone, and we'll actually look at the even terms. And so technically we're just finding the limit of the even terms, but it's not too hard to show that the limit of the entire sequence will be exactly what we get. Okay, so let's take the difference of two consecutive even terms. So let's say f of f sub 2n plus 2 over f sub 2n plus 3 minus f2n over f2n plus 1. So we want that to be positive, which would tell us that our sequence is increasing. So now let's find a common denominator and combine these guys. So notice we'll get f2n plus 2, f2n plus 1 minus f2n plus 3, f2n all over f2n plus 3, f2n plus 1. Okay, good. And now from this, we can use lemma 1. So I'll let you look closely at the numerator here. and then closely at lemma 1 exactly how you want to change those indices, but what we'll end up getting is f2 over this denominator, so f2n plus 3 times f2n plus 1, but that is bigger than 0 because f2 is 1, obviously. So here, what this tells us is that f2n plus 2 over f2n plus 3 is bigger than f2n over f2n plus 1. In other words, we have an increasing sequence. And so that will show us that the even terms have a limit, and then similarly you can show that the odd terms have a limit, and then you can argue that they have the same limit, but we're going to skip those details and then just calculate the limit of this thing. Okay, I'll clean up the board and then we'll calculate the limit. Okay, so we've argued that this thing has a limit, and now we want to calculate its limit. So let's say L equals the limit as n goes to infinity of Fn over Fn plus 1. But now notice we can rewrite that as the limit as n goes to infinity of Fn over Fn plus Fn minus 1. Okay, but now taking kind of a double reciprocal, that's going to be 1 over Fn plus Fn minus 1 over Fn. Okay, that's good, but now notice that gives us the limit as n goes to infinity of 1 over, so now we have Fn over Fn plus Fn minus 1 over Fn. Okay, fantastic, but now notice that's going to give us 1 over, so Fn over Fn is 1. Okay, so now what we have right here is essentially a shifted version of what we have down there, so we can say that this is plus L. So that gives us this equation, if we read the extreme left-hand side and the extreme right-hand side, that we can use to solve for L. So let's cross multiply, and notice that's going to give us L squared plus L minus 1 equals 0. Okay, but easily with the quadratic formula, we get L equals negative b, so that's going to be negative 1 plus minus, but we only need the plus here because obviously this limit is going to be positive by the fact that we showed that all of the terms were bigger than 0. So it's going to be plus minus b minus 4ac, so that's going to be plus 4 all over 2, but that's exactly what we want it to be. So negative 1 plus root 5 over 2, so we've established this limit. Okay, so that means we're done proving lemma 2. So I'll clean up the board and then we'll prove our main result. Okay, so now we're ready to prove our main result. Well, I haven't told you what the sum is, but we'll find out what the sum is. And we're going to do that by proving a formula for the sequence of partial sums. And you might say, well, where does this formula for the sequence of partial sums come from? And, well, I did some experimentation in Mathematica. I'm not saying that this is the only way to do it, but I did some experimentation in Mathematica until I guessed this sequence of partial sums, and then I proved the sequence of partial sums with induction. And that's what we're going to do right here. So we've got this sequence of partial sums equals 1/2 plus the 2k Fibonacci number over 1 plus the 2k plus 1 Fibonacci number. Okay, so let's do our proof of this claim. So we're going to do it by induction. So our base case will be the case when k equals 0. And then in that case, it's kind of obvious that we get s of 0 equals 1/2, which equals 1/2 plus f sub 0 over 1 plus f sub 1. So again, that's pretty obvious. So now let's make our induction hypothesis. So our induction hypothesis, so let's suppose this is true for Sk. In other words, that formula holds. And now let's look at Sk plus 1. So notice that's going to be Sk plus what we get if we plug k plus 1 into this. So that's going to be 1 over 1 plus f sub 2k plus 3. Okay, good. So now writing that out, we get 1/2 plus f2k over 1 plus f2k plus 1 plus 1 over 1 plus f2k plus 3. Okay, good. Now, what I'm going to do at this point is focus on everything in this red box. And if I can get everything in that red box to be of the right form, then we have it. And let's remind ourselves what we want that form to be. So our goal is for this to be f sub 2k plus 2 over 1 plus f sub 2k plus 3. And so that would prove our formula for the kth partial sum with induction. So our goal, to reiterate, is to get that red box to be in that right form. Okay, so what I'll do, so let's move this red box down here. Good, and now I'm going to find a common denominator and then add those guys together. So notice doing that, I'm going to get f sub 2k plus f sub 2k times f sub 2k plus 3 plus f sub 2k plus 1 all over 1 plus f sub 2k plus 1 plus f sub 2k plus 3. Okay, good. So that's what I get from our common denominator. Now the next thing I'm going to do is split this term up using the Fibonacci recursion. So I'll write f sub 2k plus 3 as f sub 2k plus 2 times f sub 2k plus 1. So that's going to give us f 2k plus f 2k times f 2k plus 2 plus f 2k times f 2k plus 1 plus f 2k plus 1 over our same denominator. So that's going to be 1 plus f 2k plus 1 plus f 2k plus 3. Okay, good. So now we have that. So we're running out of room, and I'm actually going to need the whole board for the rest of this. So I'm going to erase some of the stuff that I usually wouldn't and bring this last step, which is the red box, up to the top, and then we'll move on towards the end of this problem. Okay, so let's see where we were. We had this quotient of all of these combinations of Fibonacci terms. And now the next thing we want to do is apply lemma 1. So let's apply lemma 1 with, so let's see what we need. We need m equals 2k plus 1, and we need n equals 2k minus 1. Okay, so we're going to apply that to this term right here. So we're going to apply it to that term right there with the weird overline in red. Okay, so we're going to get a -1 to an odd power of an f of 2, so we're going to get a -1. That's going to cancel that 1 that we have, so that's really nice. So now notice that's going to give us the following for the red box. That's going to give us f sub 2k plus f sub 2k times f sub 2k plus 2 plus, and now again, rewriting that, we get we get f2k plus 2, f2k minus 1, and then minus 1 plus f2k plus 1, all over our denominator. So we have 1 plus f2k plus 1 plus f2k plus 3. Okay, so that's what we get after doing all of that. But now notice this -1 and this +1 cancel. Okay, and the next thing we can do is add these two terms and then use the Fibonacci recursion on f sub 2k and f sub 2k minus 1. And then also combine together these two terms and again use the Fibonacci recursion. So let's see what that gives us. So here notice we have an f sub 2k plus 2 term, and then these two are going to add together to give us f sub 2k plus 1. Good. And then, so those are the red overlines. but then we have plus f sub 2k plus 2, and those are going to be the red underlines. And now notice that's still over our denominator. So 1 plus f sub 2k plus 3. Okay, good, good, good. Now we can factor out an f sub 2k plus 2 here. Notice we get f sub 2k plus 2, and then we have 1 plus f sub 2k plus 1. Now this is all over 1 plus f sub 2k plus 1 times 1 plus f sub 2k plus 3. But now these two terms cancel, leaving us exactly what our goal for the red was, if you remember from the last board, which tells us that our sequence of partial sums was correct. So good. I'll clean up the board, remind ourselves what that sequence of partial sums was, and then we're ready to finish this thing off. Okay, so we proved the following. Our kth partial sum of this infinite series was half plus f sub 2k plus 2 over 1 plus f sub 2k plus 1. Okay, good. So now we're ready to take it home. So our goal, which is the sum n equals 0 to infinity of 1 over 1 plus f sub 2n plus 1 equals the limit as k goes to infinity of s of k. Good, just a definition for the sum of a series is equal to the limit of its partial sums, but that's equal to the limit as k approaches infinity of half plus f sub 2k over 1 plus f sub 2k plus 1. Great, so let's put some parentheses around that. So I'm going to bring the half out, and then that's going to give me 1/2 plus the limit as k goes to infinity. And another thing I'm going to do is be inspired by how you find limits of rational functions in calculus, and I'm going to multiply by the reciprocal of f sub 2k plus 1 in the numerator and the denominator, and that's going to give me f sub 2k over f sub 2k plus 1, and then 1 over f sub 2k plus 1 plus 1. Okay, good. So this is going to go to 0 because obviously the limit of the Fibonacci numbers is infinity, so that limit is 0. And then, now notice, this is our limit from lemma 2, so we get 1/2 plus -1 plus root 5 over 2, but now notice that's going to give us root 5 over 2. So this series, the sum from n equals 0 to infinity of 1 over 1 plus the 2n plus first Fibonacci number is root 5 over 2. And that's the end of this video.